Hello general chemistry students. This is the fifth video in week 11 and we are going to explore reaction mechanisms. So at the end of this video you'll be able to describe the concepts of reaction mechanisms, things like the rate determining step, molecularity, and elementary steps. Right? After all of this, you'll also be able to validate a proposed mechanism. All right, so what is a reaction mechanism? So we generally describe chemical reactions with an equation. And in this equation, we have all of the reactant molecules listed and all the products. But really, a reaction is really rare with more than three molecules. Because remember, we're using the collision theory of kinetics. And so typically, we have two molecules that come together to collide. So for three molecules to come together and collide with the right energy and the right orientation is exceedingly rare. So for most reactions, we will describe what's called elementary steps. And they involve one, two, or sometimes three molecules each. And their elementary steps add up to what's called the reaction mechanism. Right? And so we're going to apply these reaction mechanisms knowing a rate law of a reaction. And knowing the rate law of the reaction will give us clues into what is the rate determining step and what are those elementary steps. All right, so let's consider this reaction mechanism. So again, we have our overall reaction. Remember, that's just a collection of molecules written together with our reactants and our products. It's the overall reaction. It doesn't mean it's the mechanism. The mechanism is underneath where we have two steps, and those steps are called the elementary steps. The elementary steps are the steps that cannot be broken down any simpler. And each of these elementary steps has its own rate law associated with it. All right, and so if we have our overall reaction in blue and the elementary steps that are in red, one thing to notice here is that the compound HI is a product in step 1, but a reactant in step 2. That means HI is being consumed in the overall reaction. Therefore, we wouldn't write HI in the overall reaction because it's getting consumed in step 2. So those compounds that don't show up in the overall reaction but show up in the elementary steps, these are called intermediates. And what we do when we write the elementary steps is we can just cross out those intermediates and we can add up the overall elementary steps to give us the overall reaction. And you can see once we cross out the HI intermediate, we have H2 plus 2ICl forms 2 HCl molecules plus I2. All right, so that gets us into this idea of molecularity. So molecularity is the number of reactant particles in each of the elementary steps. Okay, and so we're going to talk about up to three, but remember a termolecular step is going to involve 3 particles, which is rare. So a unimolecular step involves 1 particle. A bimolecular step involves 2 particles, or they could be the same kind of particle, so two of the same molecules that collide together. And then the termolecular particles is one that involves 3 particles. All right, so each elementary step is going to have its own rate law. And because it has its own rate law, it's going to also have its own activation energy. So you can think of elementary steps as their very own reactions. And because they have their very own reactions, we're going to describe it in terms of its activation energy and its rate law. And the rate law for the overall reaction is going to be determined experimentally. So the elementary steps that you derive should add up or will add up to the overall reaction that has already been determined experimentally. And we're going to see that the rate law of each elementary step can be deduced from the equation of the step, okay? So here we're just counting molecules, and I'll show you what I mean. So if I look at each of these elementary steps, I have one H2 molecule and I have one ICl molecule in the first step. So I can say here that the rate is equal to K1 times H2 times ICl. That's the first step. The second step is also bimolecular because I have two molecules. So I say rate is equal to K2 times the concentration of HI times ICl. So that's the rate associated with each of the elementary steps, not the rate law overall, okay? But we're going to use the rate law of the elementary steps to determine the overall rate law, and that should match what we determined experimentally, or we have the wrong mechanism. All right, so let's look at molecularity. So if one molecule of A goes to products, that is unimolecular, and we can describe the rate law as K times the concentration of A. If we have two A molecules, that is bimolecular, and we can describe the rate law as K times A squared. If we have two molecules A and B, that's still bimolecular, and then the rate is based on the concentration of A and the concentration of B. And then there are three examples of termolecular. And remember, these are rare, but they can happen. So you either have three molecules of A, two molecules of A and one of B, or one of each A, B, and C. And you can see the rate laws associated with them. So when we describe the rate law of an elementary step, we're really just counting those molecules. Okay, so that leads us into what's called the rate determining step. So in most mechanisms, there is what's called a slow step. And the slow step is what's going to hinder the progress of the reaction or slow down the progress of a reaction. So the product can't form until the slowest step has completed. And that's called the rate limiting step. And because it's the slowest step, it also is going to have the largest activation energy. Remember, each of those elementary steps has its own activation energy. If it's the slow step, like the rate determining step, it's going to have the largest activation energy. All right, so let's analyze this reaction. So we have an overall reaction in blue, and we have two elementary steps. In these two elementary steps, we can determine their rates based on the number of molecules. So in step 1, we have 2 NO2 molecules, it's bimolecular. And in step 2, we have NO3 and CO, again bimolecular. So we also see that step 1 is the slow step, and that is the rate determining step. All right, so this is the reaction coordinate diagram that we've seen before, but remember, each of these steps has its own activation energy associated with it. So we described step 1 as the slow step, so it's going to have the largest activation energy. Okay, so the first step has the largest activation energy. And we also describe the first step as the rate determining step. The rate law of the first step is the same as the rate law of the overall reaction because we've identified that rate determining step, and that is what is preventing the progress of the reaction. So the overall rate that's observed is going to be the rate determining step here. All right, so now we're getting into the part where we can validate a mechanism. So we have a rate law that we've determined for an overall reaction. And so we want to propose a mechanism. And once we propose a mechanism, we need to validate that mechanism. And so importantly, we're validating, not proving, right? We're validating that what we're saying makes sense according to our rate law, but it doesn't prove a particular mechanism. The elementary steps must sum to the overall reaction, so we'll show a couple examples there. And the rate law predicted by the mechanism must be consistent with what is observed by the rate law. Okay, so just a couple things to think about before we do some examples. So imagine a situation where the mechanisms with a fast initial step. So the first step is fast. So if the first step is fast, then the rate limiting step may contain intermediates. Okay, and remember, intermediates don't show up in the overall rate law. When a previous step is rapid and reaches equilibrium, okay, so that means that we have an initial fast step and the concentrations of the reactants and products are not changing, then the product is an intermediate. Okay, so we have our fast initial step, our product is an intermediate. Substituting in the rate law of the rate determining step will produce a rate law in terms of just reactants. Okay, so those are some things to think about when we start practicing these mechanisms. Okay, so let's do an example. So we have 3 steps here. We're going to determine what the overall rate law is. Okay, so in the first step, so this is what we were talking about, a fast initial step, where the rate in the forward direction is equal to the rate in the reverse direction because we have established an equilibrium. The second step we're calling the slow step. That is the rate determining step. And then we have a third fast step. So what we need to do is identify the intermediates here. So our intermediates are N2, N2O2, and N2O. Okay, so we have 2 intermediates here. So we can't take the rate determining step as the rate law here because we have an intermediate. So we have to determine what the overall rate law is. And so when we do the experiment, this is our overall reaction, and we find that the rate observed is K times the concentration of H2 and NO squared. Okay, so it means we're first order with H2 and second order with NO. Okay, so now we have to prove our mechanism that we've written down based on the rate law that we observe. Okay, so let's take step 1 for example. So we know that the rate in the forward direction is equal to the rate in the reverse direction. So we can say that K1 times NO squared is equal to K minus 1 times N2O2. So remember, N2O2 is an intermediate. So we are going to solve for the concentration of N2O2 because we want to get rid of it. So we solve for the N2O2 and we end up with K1 over K reverse times NO squared. Okay, so now we can use that to substitute in N2O2 into our other rate laws. All right, so let's take step 2. Okay, so in step 2 we can write our bimolecular reaction rate law here as K2 times H2 times N2O2. Okay, remember N2O2 is our intermediate, so we need to get rid of it. But we've already solved for what N2O2 means. Okay, so let's just put that into the equation. Okay, so we are right here. we are going to take our N2O2 and just substitute it into the equation for the rate law above. All right, so now what we can do is we can just rearrange this equation in terms of our rate constants, where K2 times K1 over K reverse just becomes a simple rate constant times H2 times NO2, NO squared. All right, and you can see that that matches our overall rate law that we observe. Okay, so we have just validated this mechanism. All right, so let's do another example. So here we have an overall reaction of 2O3 forms 3 O2 molecules. The rate we observe is shown here. Okay, the rate we observe shows here. So you can see here we have a fast initial step, and we also have the rate determining step, which is the second step. So the rate for that rate determining step is K2 times O3 times O. Now we can see very quickly that the O atom is an intermediate, so we cross that out. We cannot take the rate determining step here as the overall rate because it contains an intermediate. So we have to do what we did before in order to validate this mechanism. All right, so again, let's start with step one. We know that K forward is equal to K reverse. So K forward is K1 times O3, and K reverse is K reverse times O2 times O. All right, so here we have our intermediate. We're going to solve for our intermediate. So we have K1 over K reverse times O3 times O2 minus 1. All right. We haven't seen that before, have we? A -1. All right, so now what we can do is we can substitute in for the second elementary step, which is the rate determining step. And the rate determining step again has that intermediate in it, so we have to substitute in what we solve for that intermediate. So when we do that, we have K2 times O3, and then we have this value that we solve for. All right, so if we rearrange this equation, we get something that looks like a K. So it's the ratio of the K to K1 over K reverse. And then we have O3 squared times O2 to the -1. And if we look at this rate that we solve for, you can see that it matches the observed rate law. So we've just validated this mechanism. All right, so that's all we have for the introduction to reaction mechanisms. Thank you.